Well, greetings, fellow Earthlings, and welcome to Physics 12 as we carry on in our quest to make it to the end of this school year. Um, Today, I would like to look at 5.3 electrical field strength, and that's all we're going to do. Before we start, though, if you have not looked in at the Khan Academy called Electric Field Charge, Force, and Voltage, I suggest that you go there. There's a link in Moodle to it, and watch that before you um, continue on with this. Anyway, so come back if you haven't, and if you have, let's carry on. I want to begin with a few definitions and concepts of what we mean here. A field is a region of space in which a quantity has uniform value. So this is a region of space in which a quantity has a uniform value. An electric field is a region of space in which a charged particle or charged object, in which we're going to be dealing mostly with particles, but let's say a charged object, is acted on by a force. A test charge is considered to be an infinitesimally small particle, charged particle, acted upon by a source charge or electric field. So this is an small charged particle, and that can be a plus or minus charge, as can be the source, acted upon by a source charge. Or electric field. Electric field lines, properties of electric field lines. We're probably going to, I don't know if it's worth writing anything there, because there's a property list of, and this is to do with field lines, down below. And this is, field lines indicate direction of the electric field. The second point is the closer the lines, the stronger the field. And field lines generally are arrows, or and the arrows point in the direction that a positive charge would move. Positive test charge. Okay. And the I'm going to put a D here, and generally what that means is that if this is positive, this is a positive charge, then the arrow is going to point away from it, and it points towards a negative charge. Okay. So how do you feel about that? Well, when we look at the diagrams on the next page, it will make a little bit more sense, I think. Okay. So here we have, on this side here, these are, we have two point charges here. There's a point charge here and a point charge here. And you can see how these lines go. If you consider how close these lines are compared to here, it's stronger here. So this area here, because they're close together, this shows this is stronger here. And the same is true as you get closer to this negative charge. This is stronger as well. And then in the middle, this is weaker. So the overall attraction, oh sorry, this weaker would be in here. This area here would be the weaker part, okay? And the overall attraction though, or the overall force in this situation is towards each other, okay? So this is the direction that it's going. When we look at two like charges, everything is the same. We have it's stronger closer to the source. Lines are drawn closer together in both cases. Okay. And as you go out, the lines spread out and they get weaker farther out. Okay? and basically there's less directionality here. So these we have two similarly charged particles, and you notice that their force is actually in opposite directions. They're going to actually repel each other instead of being attracted to each other here. Okay? Let me see now. Quick check. I've got a note here. Quick check 5.3.1. The 5.3.1, it says draw, and this is on page 180. And so it says draw and label a sketch of each represented by the celery seeds in figure 5.3.5 and assume the wire on the right is positive. So okay, so just looking at the first ones, we have I'm just going to do one of these, and let's see, 1A, we have a positive charge in the middle, and so the field is going to look something like this. Nice sketch, eh? In B, we would look at B and we'd say that these are two oppositely charged, and the one on the right is the positive one. So basically, it's like this, and so this one is going to be toward the negative, and this probably something like that. You could probably make these things arcing too, so that's fine. Okay. C, you can see that they're repelling, so these are two like charge poles, and they're always saying the one on the right is positive, so they're both basically we're going to be redrawing this guy. Something like that. And these are so these are two wires that are going down, and again the wire on the right is positive, and because there's an attraction between them, it's going to be a negative, it's going to be a positive. And so on this one, this is going to be the field is going to go out like this in both. Make sure you get the arrowheads going in the right direction here, and then so it's going towards the negative. Arrows go towards the negative, go from the positive. So it should be something like that. Okay. Question 2 is pretty much the same as this, those two positively charged. And 3 says a strip of vinyl is rubbed with fur and a strip of glass is rubbed with wool. Draw the electric fields that occur when the two charged objects are brought close together and parallel to each other. So in number 3, what you have to do is you have to go back to the Triboletic effect and to see what happens with if you rub these two together, pairs together. So if you rub vinyl and fur, if you rub those two together, you get this leads to a negative charge on the vinyl. Okay? If you take glass and wool, you rub those together, you get a positive charge on the glass. Okay? So they're looking at these two. They're saying, so if you've got the vinyl strip here, this is negative, and you've got the glass, that's positive. Basically, you're going to get the same thing going on here. So you're going to have an attraction going on, is what I'm saying. So like that. Okay? Okay. Geez, we did check 5.3.1. Okay, let's look page over. This is electrical field strength. And so in the same vein as what we did on the page 1 when we talked about the distance between arrows gives an indication of strength and weakness. On the first page, what we're looking at is point. These are what called point sources, okay? And there is a field around them, but we're going to be looking at uniform fields. And so this is basically introducing, these diagrams are introducing a uniform fields as opposed to points. So these two guys on this side, these are point sources. Okay, you can see they're both positive, they're both going the same direction. So these ones over here though would be, for example, between two plates. And we'll revisit this later on. And so this is going to be the positive plate, and this is going to be the negative plate on both of these. So what this is indicating here is that you have a stronger field between these two plates than between these. Okay? Now, when we're measuring these strengths, whether it's around a point or whether in a field or between plates, then we use this equation. E stands for the electric field strength and it is equal to the force in newtons divided by the charge in coulombs. This is charge in coulombs. Okay? Let's look at a sample problem. I'm going to use crumpled paper, eh? So the sample problem is 5.3.1, and that is on page 181. So the sample problem goes like this. You're given a positive test charge of 2.2 times 10 to the minus 8 coulombs and a force, experiencing a force of 1.4 times 10 to the 3 newtons towards the west. What is the electrical field position? Well, you're given Q and F, and you're asked to find E. So it's just, you just plug and play, and you get a value of 1.57 times 10 to the 5th newtons per coulomb. The practice problems that are below are the same kind of idea. You're asking, so what charge exists if you have this force and this electrical field? Well, all of these problems are just taking, they're just taking the equation E, oops, sorry, you can't see that, E equals F over C, and they're giving you two of them and saying solve for the third. So in this case, they're looking for the charge, and so to solve for charge is going to be equal to the force divided by the field strength, and so the force is equal to 1.80 times 10 to the negative 8 newtons divided by the electrical field strength of 4.00 times 10 to the minus 4 newtons per coulomb. And so you'll see that these cancel out, the newtons cancel out, and the coulombs goes to the top, and that will give you the answer. I'm not going to bother doing it. I just want to show you really how simple this is. The other problems here are the same. They're giving you Q and F, solve for E. They're giving you E and Q, solve for F. So it's just a question of plug and play on that, okay? And that is all I'm going to say about that. Put this back in my folder. Put that away. Last thing is the magnitude of the electric field around a source charge. Now, when we're talking about the magnitude of an electric field, this is going to look kind of funny to you, but we don't consider a second charge, because we don't have a second charge. We just want to know what the field strength is at some distance. And so basically, you recall that we've seen this before, where we want to find what we've used, what's that, the Coulomb's constant, and normally it would be the larger Q divided by the smaller Q, but it turns out that we're not looking for that at all, so we don't consider the second charge, and none of the problems will say that. They'll just say, what is the field strength at this distance? So when you get that, basically you're just looking at the source charge. You only need two things. You need the value of the source charge, which is this. That's the source charge. And this is the distance. This is going to be in meters. This is going to be in coulombs. And so, so you're going to use the Coulomb's constant, which is 9.0 times 10 to the 9 Newton meters squared per Coulomb squared, and that will give you the electrical field strength. Okay, so basically what I'm saying is that suppose that this is a source charge, and the source charge has an electric field that has diminishing strength the farther you move away from it. Okay? Like so, like so, like so. So intuitively, if I was to put a, let's say I put another test charge here, close to here. Because this distance is small, and because the force, these arrows are close together, this is going to have a stronger repulsive force. I'll put a little plus there to indicate that this is, than if I put something like, say, way out here. Okay? And so what you're trying to do is you're not talking about actually putting any point charge in here. You're just saying what would be the field be like here as opposed to farther out. And that's why you ignore any other cue. Okay? So when we're looking at the quick check problems for here, it's basically the same kind of thing. Let's look at where's quick check? Okay, so on page 182, I'll just show you what I have here, so you can maybe what we can do is let's put quick check. We'll write quick check problem, the first one in let's do number 2, because I've not done it yet. So no, I need my calculator. It's not going to work in here. Forget it. We'll do number 1, and then I'll get you to stop the video, and then you can go back and do 2 and 3. They're the same. They're just plug and play. Just be careful that when you are using units that meter distance has to be in meters, not centimeters, and the like. Okay. So it says, what is the field strength at a distance of 0.75 meters away from a 90 microcoulomb charge? Okay, so what we know is we know that R, or D, is equal to 0.75 meters. We know that K is equal to 9.00 times 10 to the 9th Newton meter squared Coulomb squared. We know that the charge Q is equal to 90 microcoulombs. Well, what's a microcoulomb? It's 10 to the negative 6 coulombs. So what I do is I leave it like this. I just write 90 times 10 to the negative 6. Really, it's the same as 9 times 10 to the minus 5, but you know me, I make mistakes easy. So now all I want to do is I just take these values, plug it into my E equals K Q over D squared, and this becomes 9.00 times 10 to the 9th. I'm not going to bother putting in the units, times 9 90 times 10 to the negative 6 divided by 0.75 squared, and I don't know what that comes out to. You can run that through your calculator. So that's basically all we're doing with that. Okay? That is quick check. Oh, it comes out to, I've got it done here in another paper. That comes out to 1.44 times 10 to the 6 newtons. Wow, that's a lot of newtons. Okay. The other two are just same kind of thing. They're all plug and play. They're asking you to, they give you different values, and you just solve for the unknown. So that's pretty straightforward. Okay. Sample problems on 5.3.2. I will let you. Oh, no, I'll put up. And so this is where you have multiple charges and looking at what the effect is on a third charge. Now, in this case, we have one charge here that is a positive charge, 3 times 10 to the negative 6 coulombs, and here's another positive charge at 1.5 times 10 to the negative 6 coulombs. And they're asking what is the net force which is acting at a point P. Okay, so what is the force that is here? So in order to do that, you need to solve for both of them. Okay. Now the moral of the story here is they're both repulsions. So if you look at A, if you substitute for A, the coulombs and halfway point. Okay, so you're trying to figure out what's happening at 30 centimeters or 0.30 meters. But you're asking, this 0.30 meters is what effect is it having on here, but you're asking what is the effect here, which is halfway, so it's 0.15 meters. So if I plug that in, I come out to this value here. Okay, 1.2 times 10 to the 6 newtons per coulomb. If I plug in these values, which is half of that, I come out to negative 6 times 10 to the 5 newtons per coulomb. Now, why the negative? Well, because it's a directional thing. We've applied positive in going from left to right. So that's positive. So going from right to left is negative. Okay? Now, intuitively the larger charge, the 2 times charge, which is 3 times 10 to the negative 6, it's going to have a larger effect on P than the 1.5 times 10 to the negative 6 is. So the net force is going to be the A, the force generated by charge A, plus the electrical field produced by charge B. And what we do is we add those two together and we come out with the net. So it's the sum of the two. But in doing so, you have to remember that this is negative. Okay? So in some ways, you could think of it as either the sum, but keeping in mind that there's a directionality difference, or you can think of it as the difference between the two. Okay? I just mentally, I prefer to think of it as the difference between the two. It makes more sense to me somehow. I have a hard time wrapping my brain around the rest of it. I'm going to get you to, I'm going to let you look at the practice problems. This one, number one, is confusing as heck. And to be honest with you, I do not know the answer. I can't rationalize the answer. If you look at the back of the book, I think it says that there is no force. I'm not sure, or no electrical field. I'm not sure. At Q, I'm sorry, at this point here. But to be honest with you, I can't understand it. And I've looked at it, and I've tried to think about it in the most simplistic terms, and that's why you see all my drawings here. Because the confusion, it says, it shows a positive charge located near a smaller in magnitude negative charge. Now, is that talking about this? Or is that talking about this? So if this is a smaller in magnitude, a negative charge, then the force is going to be like this. It's going to be like this, like so. Okay. Now, it says circle in the Roman numeral that represents the region where electric field due to the two charges is equal to 0. Okay, so you got 4 possibilities. You got this one here, you've got 2 here, you've got 3 here, and you've got 4 here. And I'm not positive. I'm just going to check to see what the score key at the back says. It says what? Page 184. It says 3. It says that there's no charge here, or no the electric field is 0. Now I can't see that because there's got to be some. These arrows indicate that there is an electric field. Okay, there's an electric field going on here. So I can't understand that. These arrows indicate there's an electric field. These arrows indicate there's an electric field. These arrows coming in indicate there's an electric field. So I don't understand how they can say that. The only thing that I can maybe rationalize is that because this is a positive charge, a large positive charge, and this is a smaller negative charge, that it's going to basically, the strength of these two is basically going to be maybe weaker over here. I don't know, but it's not going to equal 0. If you can figure this out, please let me know, because I am absolutely bamboozled by that. I'm going to show you the solutions for 2 and 3 here, and just as a to get you going in the right direction. So it says, what is the net field at point P between the two oppositely charged spheres in figure 5.3.10? So what you might want to do is pull out your text and look at this, and once I put the solution up, maybe stop the pause the video and see and take a look at it and try to rationalize it, or even copy it down or take a picture. So here's the solution. So I recommend that you always start by drawing what you have. -2 microcoulombs here, plus 44 microcoulombs here, distance of 4.2 and 1.9. So I solve for both, as this is laid out, I solve for A, the electrical field strength for A, using these by plugging it in. Okay. And I come out to -1.02 times 10 to the 4. Okay, because this says negative charge, so the negative charge. Positive charge, 1.1 times 10 to the 5 newtons. Okay, so the net is 1.2 times 10 to the 5 newtons to the, for some reason I had left there and I could scratch it to the right. So looking at stronger attractive force, I guess, to the right. So here we go. Okay, I'm going to put up the other one, the next one. 3. Here's 3. I'm going to let you take a picture of that or do whatever. And then I'm going to call it. We're at 42 minutes right now, so that's enough for today. You're up for 5.3 review questions, so this should be due by the next block, which is would be 2 days away. I strongly recommend that you maintain a regular schedule, same schedule that you would normally. So 2 days hence, review 5.3 would be due, and and at that day you should go on to the next unit, which is going to be 5.4, and then we will play it from there. Okay, I don't want to kill you guys right away. We'll speed up a bit as time goes on, but I think you may need to go back, do a bit of review of 5.1 and 5.2, and pick up today and spend a little bit of time. Next day, 5.4, and then the day after that, I'm going to be doing 5.5 and a special unit on cathode ray tube calculations. Okay, getting help. This is going to be a bit messy, but my suggestion is that you email me or text me or do something what questions you want answered, and I will try to have that ready for you. There's regular office hours, so I'll be available, and I will try to be ready for you on those days. What I may do is email you a solution, or take a picture with my camera or my iPhone and send it to you that way. I'm not sure exactly how I'm going to do it, but I will need advance. The Zoom is not good at just doing stuff on paper in front of your eyes. This is the best way to do it, so we may have to resort to this. Anyway, bless you, and we'll see you next time. Bye now.